Hey guys, welcome back. Day 11, Quantum Theory. And we're going to start with characteristics of waves. Right? So if we remember, wavelength, right, is the distance between two identical points. So it doesn't matter what 2 points. It could be the top, which is the crest to the top. It could be an intercept, the same intercept. It does not matter where they are. It's just distance to the closest identical points. Right? So like if this was y equals sine x, for example, if you ever graph that. All right? So this point right here corresponds to this point right here. It's the same spot. And so one wave would be from the origin here, right, up and down there. That's one wavelength. Okay, that's leads us to frequency, which frequency is the rate at which the waves are passing a certain point. So it's how many oscillations in a second. Cycles per second, hertz, 1/second. This is the same thing as 1/second. You might also count a wave number, which is 1/wavelength, which is in centimeters. Centimeters -1. Or period, which is time, 1/frequency. All right. So there's two main types of waves, right? Traveling waves and stationary waves. Water waves travel, sound waves travel, light waves travel, but there are also stationary waves. All right. And so an example would be a violin string. Maybe you've done the ropes in a gym, right? And so if you've done the ropes in a gym, that's a standing wave, right? Stationary waves. So the conditions must be continuous. We can't be broken. It can be fixed at both ends, single valued with no loops. So let's look at a couple of these. All right. We have 1/2 the wavelength. So if the length here, so this distance, the length would be 1/2 of lambda. Right? 1/2 of lambda means that sine wave would go up and come back. All right? That's 1/2. If the length becomes, right, 2/2, or 1 lambda, the wavelength is lambda, what happens now, and I'll use a different color, is that we go up and down, and then we come back. And right here is something called a node, right, where it's 0, right? Then also if we have L, and L is the distance from this line to this line, right? That's the distance. L is equal to 3/2 lambda. Oh, that was supposed to turn blue. Okay, we get, and I'll do this one orange. I'll try my best to draw this up. Perfect, and then coming back. Great. Well, there's 2 nodes. All right. So that's a violin string, and the thing is, the vibrations are quantized. I mean, I can't just be anywhere. I have to be at half or whole integer parts of the wavelength, right? So we got to be a whole number there. N's a whole number, right? You can't be 2.3. And so this picture over here talks about a drum where you have n equals 1, n equals 2, n equals 3. So the first one's a violin string, right, or guitar string. The second one's a drum, all right? And then we have L equals 0, L equals 1, L equals 2. All right, and so this is a drum surface, and how kind of the drum surface would be waving, so to speak, when you hit it. I'm not a drummer. Maybe you are a drummer. Maybe you're not. All right, so N is the total number of nodes, and L is the total number of planar nodes. All right, and that doesn't really make sense to you. That's okay. You're not going to be tested on it. But you're now in 2 dimensions versus 1 dimension. And quantum mechanics actually happens in 3 dimensions, so it's even more fun. All right, I'm not going to dive too much into that. It's just a picture. If you're interested in it, I'm sure you can find more on it, because you guys, again, aren't going to be using it much. All right, we are going to go into Heisenburg right now. And Heisenburg comes in with the uncertainty principle. Because if we go back, we step back, what are we looking for here? We're looking for where the electrons are and what behaviors are they doing so that we can predict behavior of the atom. That's ultimately the whole goal. We don't really want to like care that we don't care about them that much as long as we predict behavior. And the problem is observing them is where we're having a big like gap in our goal. So when we observe something, you need to shine light on it somehow. So sunlight could happen, right? So like we have flashlights, we have artificial lights, we have X-rays, radio waves, and so all these waves we've had, like early radar. World War II, the Britons, they had radar, and so that was a huge advantage for the Royal Air Force over the Germans. All right. So radio waves, they help us see objects like planes and whatnot, right? But you can't see objects smaller than a meter. Microwaves, there's actually microwave radar now that people use, and you can actually see very good resolution. Visible objects, we can see objects as small as micrometers, which is why microscopes, we might not be able to see with the naked eye, but we can see things under microscopes pretty well. X-rays, we begin to see molecular structure, right? Because the wavelength must be as small as the object we're observing. Okay, so it's hard to see a lot of humans with radar. Microwaves, not a problem. Now we don't want to use too much microwaves because it does cook us. But right. Visible light, we can see people. You have very high resolution of most of the objects we touch and deal with because our wavelength we're using to look at our objects is so much smaller than the actual object. All right. So with X-rays, we get to see the molecular structure. So the uncertainty in the position of the object we're talking about, right? So if you have a pen on your table, let's say, or your phone's on your table, the uncertainty where that phone is not very uncertain. You see exactly where it is, high definition, unless of course your eyes are out of focus, right? Because you don't have glasses on or something, right? You have very high precision where that phone is. In fact, the uncertainty is proportional to lambda. So you're talking micrometer precision, which our eye can't perceive. So we have extremely good position where things are. Right? So the smaller the wavelength, the greater the precision, and the smaller the uncertainty. And so that's how people can play baseball and hit that ball that's going 90 miles an hour, or softball that's going pretty fast too, right? In such a short distance, and they can hit it, and it's pretty neat. All right. So why not use radiation with a very small wavelength? All right. So think about this. The hydrogen atom is about 100 picometers across. Right. So if I have H, if I had a sphere, it's about 100 picometers across. Right. And you get an electron in there. So why don't we use an X-ray or something even higher energy, smaller wavelengths, much smaller wavelength to look at that? Well, a small wavelength, a high frequency, a high energy photon. Well, what does that mean? All right. So this electron, if I'm gonna draw it as a sphere, I don't know what electrons look like, but let's just have a sphere here. There's my electron. Okay. And I'm going to have a high energy photon. So first of all, the mass of my electron is 9.11 times 10 to the negative 31 kilograms. That's the mass. Here comes my photon. We'll do it. Photon. And it's coming in. Comes in. Boom. Observed, right? You got a hit. We got a collision here. Well, it turns out to be a huge collision, right? Well, what's going to happen is that this electron will be moved. And here is delta x, right? There's a huge collision there. Huge collision, right? It's a transfer of momentum. It's kind of like pool, billiards, right? There's a transfer of, of momentum. So what happens is that the change in this position times the change in the momentum, which would be, let's call it m. The mass doesn't change, but the velocity can, delta v, is going to be greater than or equal to h over 4 pi. All right, so remember, we have the Broglie wavelength, we got momentum. You can derive this. I'm not going to worry about you driving this, but this is your uncertainty principle. Okay? So what that means is we cannot know both the position, right here in green, and the momentum, right here in orange and pink, at the same time. So there's a limit of what we can observe with the electron because it's so small. We shine too much light on it, too intense light, that small wavelength, but we move it, right? And that's not a good thing, right? So fortunately, though, h is small, and so the uncertainty is only evident when the mass of the object is very small, right? So when you shine light on you're looking for your kid, you're looking for your dog, a cat. Shine light on the cat, you see the cat, right? It'd be horrible if you shine light on something and then the object just flew away. That'd be horrible, right? But that's what's kind of happening here. Okay? Because even if it moves 5 picometers, that's a huge difference. 100, right? That's 5%. Okay? I don't know how much it moves. You'd have to calculate that. I don't know what that would be. And it would depend on the light shining in, but it would be a big deal. All right, so let's look at this first of all. I have this example here about the electron in the hydrogen atom, and we're going to make a little bit of approximations here. We're going to overestimate so that we make sure our example, we're going to overestimate it so that even though it's going to be too much, it's still going to be good for our example. Okay. So if this is a hydrogen atom and this is 53 picometer radius, I think it says, yes, 53 picometers, and the electron's traveling at 2.19 times 10 to the 6 meters per second, which is less than 10% of the speed of light, which is good, right? That's the H atom. So we want to know, first of all, how far is the orbit? So let's say the electron's here, and it's going to go all the way around. Well, the circumference of the circle is pi d, or 2 pi r, right? 2 pi r. So 2 pi r would be 2 times pi times 53 times 10 to the negative 12 meters. All right? So 2 times pi times 53 times 10 to the minus 12 happens to be 3.33 times 10 to the negative 10th meters. That's the distance the electron would go. Right? And if you remember, distance is velocity times time. So 3.33 times 10 to the negative 10th meters is 2.19 times 10 to the 6 meters per second times t. Alright, so we divide by 2.19 times 10 to the 6, I get 1.5 times 10 to the negative 16, 1 over seconds is the time. No, seconds. Seconds, not 1 over seconds, seconds. I want 1 over seconds. So that's the time. That's it. So it's 15 zeros 1. So how many, if I inverse this, right, 1 divided by 1.5 times 10 to the negative 16, 1 over seconds, I actually get a period, right? And that happens to be basically, let's just call it 6 times 10 to the 15th rotations per second in one dimension. All right? In one dimension. So that's a lot of rotations per second in one dimension. All right? So if I'm going to rotate, that's rotations per second. That's a lot of times in a second. So in 1,000, it went around 6 times 10 to the 15 times. Now, if I divide that by 360 for 360 degrees, let's just say it's 2 times 10 to the 13th rotations per second. Let's even do it 1 times 10 to the 13th rotations per second in 360 degrees-ish. All right, that's still a lot. That's over 1 trillion times a second it goes around the atom. All right, so it's going ridiculously fast in a very, very small space. So the point of this exercise is just to get a ballpoint estimate that this goes around the atom trillions of times in a second. Now, its orbit's not like just a ball going around. That's not how it really works. Okay, that being said, for our purposes, no matter what, no matter how I'm coming in, right, to the atom here, if I come in here, if I come in here, if I come in over here, if I come in over here, no matter what happens, I am hitting that electron. I'm going to hit the electron. It's almost like, it's like a helicopter rotor, so to speak, right? Or a propeller. But it's going way faster because those are in the thousands of rotations per minute. We're in the trillions per second. All right? So, big, huge difference, right? There's a big difference between having $1,000 in savings and $1 trillion in savings. So, right, this thing is, no matter what happens, whether I shine light at it, whether I do anything, what we hit is the electron. All right. So since it's moving so fast in such a small area, and we can't actually get a picture of where the electron is, that's not possible. All right. Some very smart people, smarter than me. 1926, Schrodinger and his cat. Some of you guys know his cat. There's a kind of funny little thing in the Big Bang Theory where the actor does a pretty good job explaining Schrodinger's cat, right? But he said he's going to treat the atom and the electron as a wave in 3 dimensions, right? Which is kind of fun, right? And so he has, now it starts off with H psi equals E psi, and it goes from there. So it starts off with H psi equals E psi. Okay? Oh, it just disappeared on me. H psi equals E psi. Alright, so what are these? H is a it keeps, oh, that's because I have this pen. Sorry. H psi equals E psi. There we go. So H is the Hamiltonian operator. Capital H for Hamiltonian. It's a set of equations that transforms one um, well, it transforms one equation or one function into another, and it represents the total energy of the electron in the atom, both the kinetic energy and potential energy. All right. So this psi here, this is the wave function. All right. Okay. It describes. It's a function. It describes. Right. The wave-like characteristics. There it goes. It's a mathematical function that describes the wave. Right. The wave-like properties. And of course, E is the actual energy. Okay. So an operator, just to note the operator, an operator would be something like d over dx of x squared. Right? That green is an operator. You're taking the derivative of x squared, and your new function now is 2x. All right? So the derivative of x squared is 2x. Maybe you know that, maybe you don't, and that's fine if you don't, but that's all an operator is. Now, this equation up here gets really deep, like the next step. So we're just going to stop there. All right? But you guys know some of these, so let's draw. If I could xy here. Right? You guys know what y equals sine x looks like. All right? So that's y equals sine x. All right? Well, getting to a standing wave. All right? The standing wave here looks a little bit different. It's where we have a wave that goes up, hits that point, comes back. Or, right, we did those earlier, where this is L from that point to that point. That's the length. All right? And so we found that the wave function does something like this, where we have our graph. And again, don't stress too much about the graphing. Okay, don't worry too much about that. But this graph here from the wave function, it talks about the distance from the nucleus that the electron is. So very low, high probability, and it does something like this, right? And so, and these are these equations. You won't use, unless you take a junior level chemistry class, you're never going to use them, and that's okay. All right. The point is, what does all this mean, right? Why, like, great, all these details, all this stuff. What does this mean? What does the wave function mean? What does psi mean, right? And how does it describe the behavior of electron? Like, great math, wonderful, right? We want to know the probability of finding the electron. And the thing that is hard to grasp is that these things are not like objects we observe. So I live kind of not too far from the beach, the ocean. And there are sharks in the ocean. And so my probability of me in the office, my office right now, having a shark attack, regardless of what the Sharknado movies say, right? Very low. It's zero. There's not going to be any sharks in my office, right? There's no chance a shark's going to swim to my office, right? But if I go to the beach, my chances go up because that's the ocean, right? Now, if I don't go in the water, I still have a very, very low chance. That would be a very low chance of me not being in the water at all. All right, and there's certain parts where, certain times of day and all that other stuff where those factors happen. Tonight, At 2 in the morning, there's a very good chance that I'm going to be in my bed. It is not zero. I have 3 kids and a dog, right? I might get up and have to use the restroom. Like there's things happen where I might not be in it now. Odds are in the bed, right? But there are days where I've not spent the night in my house. Maybe I'm on vacation. Maybe I'm at a conference, right? And so there there's there's not a 100% chance that I'll be in my house even tonight. Because the dog has to go out and I step outside, I'm not even in the house at 2 in the morning. All right. Conversely, there's a very high probability that right now I'm not home because I'm not home. But there is also that chance that at this time of day I'm home. So there's probability of finding me. Where's the probability of finding me? Okay, and the probability of finding me from my house as you put radiuses out, right? The chances of me finding me are less and less. And so psi squared represents the probability of finding the electron per unit volume around the nucleus. And that's what we really care about. Where is it? Now, I just used that example of me and the sharks and whatever you're trying to find. Electrons are not they're quantum objects. They're not macroscopic objects like a baseball. So in fact, I have played baseball before. I like being in the outfield. I was pretty good at catching fly balls, and I could tell where that ball was going to go. I'm pretty good at catching them. All right, even with the wind and the spin, depending on your left field or right field, center field, how it came off the bat, right-handed batter, left-handed batter, I could catch them pretty well. All right, I was actually much better at fly balls than ground balls. Ground balls are not my thing. So I could do that, and I could see where the ball was going, and I can see its trajectory, and I figure out exactly where it's going to land, catch it, and go. Throw it in. Great. Electrons don't behave this way, right? Just because it came off the bat, so to speak, it doesn't necessarily mean that I can look at its trajectory and predict where it's going to go, which is very weird, right? This is the hell quote that you've probably heard that Einstein said, "I don't believe God plays dice with the universe," or something like that. Well, there's probably more to the story than we even know, right? But that we don't live in electrons aren't deterministic, which is really weird. Okay, but we care about the probability of finding the electron per unit volume in the space around the nucleus and how these are. All right, so this leads us to the quantum numbers. Okay, so if you actually solve this math, so we just did the whole, not even the tip of the iceberg. We just said icebergs exist, didn't even show you what they were, and now we got 3 solutions. Okay, all right. There's 3 solutions. There's N, which we've been talking about. There's L, and there's M sub L. All right. So N is our principal energy level. All right. It's our energy level. And N equals 1, 2, 3, technically all the way up into infinity, although you're not going to have, 15,000th energy level of a hydrogen atom. That's not going to work. But technically it's there. L is the secondary. Oh, I wanted blue. All right. And L can be 0, 1, 2, 3, all the way to n minus 1. And that's our shape of the orbital. Okay. And then you have your magnetic. M sub L is negative L to positive L. And that's our orientation. All right, so those are our 3 numbers, these 3 letters that come out of the orbitals, and we're going to talk about that in the next one.